beam. This is a cantilever beam of length L, which is fixed at end A and free at the end B. Let a concentrated load W is applied at the free end B, and I have material property E, and I as a second moment of inertia of cross section of this beam about its neutral axis. So what is given? Length of the beam is given as L. E is the material property, that is Young's modulus, and capital I is the second moment of area of cross section of this beam about the neutral axis. And we are asked to find out delta B by using Castigliano's theorem. Deflection at the point B by using Castigliano's theorem. Now, in order to solve this problem, in order to get a deflection at the point B, I take a section XX at a distance x from end B, like this. I take a section XX at a distance x from the end B. So if I draw free body diagram of this portion, this is end B, and here the concentrated load W is applied. This section has length X. Here is the shearing force Vx, and the bending moment is Mx. So this will be the free body diagram of this portion of the beam, this portion. For this shaded portion, I have drawn free body diagram here. Vx is the shear force and Mx is the bending moment. If this beam is in equilibrium, and of course it is in equilibrium, then every portion of this beam is in equilibrium. So now the beam is in equilibrium, therefore this portion, this free body diagram portion, must be in equilibrium. So balancing the moment about the section XX, I am balancing moment about this section XX, moment balance. About the section XX, I will get summation Mx equal to 0. This is capital X denoting the location of the section. This is the section, capital X. So I will get Mx plus W into X equals to 0, and therefore Mx equal to minus W into X. We know that the strain energy stored in a beam of length L is given by U equal to integration 0 to L mx square by 2EI into dx. This is the formula that we have derived in the last lecture. U equal to integral 0 to L mx square by 2ei dx. So replacing mx, integration 0 to L, integral 0 to L, and the value of mx is minus w into x whole square divided by 2 times ei dx. So u equal to integration from 0 to L w square x square by 2ei into dx. Now w is constant, e is constant, I is constant. I can take these quantities outside the integral. So I would get w square by 2ei integral 0 to L x square dx. So u is equal to w square by 2ei, and integration of x square is x cube by 3 between the limits 0 to L. And by putting the limits, I will get w square by 2ei into L cube by 3. So this is an expression for strain energy. We have calculated strain energy stored in the entire beam. Now, according to Castigliano's theorem, we have according to Castigliano's theorem, we have delta P is equal to dou U by dou W. That means the partial derivative of strain energy with respect to the force gives us deflection at the point of application of force, and the deflection would be in the direction of force. So as the force applied is vertical, we would get the vertical deflection at the point B. So delta B is equal to dou by dou W of U. U is already calculated, W square by 2ei into L cube by 3. So this is the value of capital U, that is strain energy. And if I take the derivative, I would get delta B equal to derivative of W square is 2W divided by 2ei into L cube by 3. And if I simplify this expression, I would get delta B equal to W L cube by 3ei. So in this way, we have calculated deflection at this point B by using Castigliano's theorem, and the procedure is very simple. Let us have a recap over the procedure. I have taken a section XX, capital XX, at a distance x from the point of application of load, and considering the equilibrium of this portion of the beam in this following diagram. Here I have drawn free body diagram for this considered element of the beam. and mx is the bending moment at the section xx, and vx is the shear force at the section xx. And balancing the moment about this section xx, about this edge, moment is balanced, and we get mx equal to minus w into x. And we know that the strain energy of bending is given by this expression, u equal to integral 0 to L mx square by 2 ei dx. And replacing mx, here is the value of mx we have calculated, bending moment at section xx, that is integral 0 to L minus wx whole square by 2 ei dx. This minus wx is the value of mx. And by simplifying this and solving the integral, I get capital U equal to w square by 2 ei L cube by 3. This is the strain energy of bending, and this strain energy of bending is differentiated with respect to the load W, and I got delta B. But important thing is that here we have considered strain energy of bending only. The strain energy due to shearing force is not taken into account. It is because the strain energy due to shearing force is very small in comparison with the strain energy of bending. Thank you.